All right, so the last thing that we have to do, as I said, the last thing we have to do is hydrostatics, and then we're going to spend some time and review this whole thing, right? So pressure, we should remember what pressure, right? In case you never heard about pressure, pressure is your force acting per unit area. So if, for example, if you have the ground and you are applying a force, like on a nail, you're applying a force, the force acting per unit area gives you pressure. Pressure is force on area, is measured in pascals, SI unit is, and that's wrong. Oh wait, no, that's right. NM minus 1. Wait, no, that's wrong. That should be squared. It's NM minus 2, sorry. Okay, so the SI unit is Newton per meter squared. All right. One thing I want to notice is that the smaller the area, the greater is going to be the pressure exerted. All right. So for example, if you're walking in a shoe with a flat sole, you will exert less pressure than somebody walking with a high heels. All right, because the area of contact here is smaller. You can also do the example with your pencil. If you apply the same force with the pencil tip on your finger, it will, of course, hurt more as opposed to the other way around. All right? So the smaller the area, the greater the pressure, provided that the same force acting, right? So that's some of the things that we need to know initially about pressure. For a constant force, pressure on a solid depends on the area. A small area exerts a larger pressure than a large one will, right? So for example, if you have a nail is defined. All right. Don't know where I put that, but a nail is defined with a pointy tip so that it will exert a large pressure when exerted into the wood, right? If you look at an example like a knife, let's say I had a knife looking like that, right? Which side is sharp side? The underneath here. This is the sharper side, right? Why? Why is this side underneath there the sharper side?
It has a point, like it's pointy.
Right, so the area here, the area is smaller. Right, so yeah, you can say point here, but the area is smaller. So the part underneath is sharper because it exerts a greater pressure. Right, so this side exerts a greater pressure. All right, so the main thing I want you to learn is that the smaller the area, the greater the pressure. Okay. All right, nice. Right, so that was pressure on a solid, right? But this evening I passed by. Pressure in a liquid. So we initially looked here. This formula only operates or only applies to pressure on a solid. Okay? Pressure on a liquid, on the other hand, pressure on a liquid, on the other hand, is defined by root GH. Pressure in a liquid is density by gravity by depth. So what does that mean? It means that pressure in a liquid is dependent on the density of the liquid, gravity, and the depth in the liquid. Okay? So if I give you a liquid here, and you were here, and somebody else was down there, the lower you go, the greater the pressure. So that this person here has a greater pressure acting on them as opposed to this person here, right? So down here, you have a greater pressure, right? And the main reason is that you must slow down, okay? So the greater the depth, the greater the pressure, all right? So that's something I want you to remember when we're dealing with pressure in a liquid, all right? Although you have the notes, just make a note of the little formulas, right? Density by gravity by depth, that's pressure in a liquid. And pressure in a solid is force on area. All right, nice. The formula implies that the lower we go into a liquid, the greater the pressure, right? We have these two basic experiments to always be able to explain. Pressure varies with depth, and pressure, the same horizontal level is the same, okay? So we need to be able to show that. I'll do it here for you. Sean, what are you doing? It's last start now. Yeah, let's take it out now and get plan on thing. Right, so pressure varies with depth. So the most popular experiment is this one here. Right, so the most popular experiment is this, right? Fill a container with water and have 3 holes at the different depths. What do you think will happen? 3 different, yeah, you have 3 holes there at different depths. What do you think will happen to the water coming? Of course, water will come out, right? What do you think will happen? Right. The water at the bottom will come out the furthest because pressure is the greatest down there, right? Here is in between, and here is like that. That's okay? That's the experiment to show that pressure varies with depth. But what you will do for pressure at the same level, pressure at the same horizontal depth is the same. What you'll do, how you will vary the same thing. What you can do. Any guess? Caleb? Pressure at the same horizontal depth is equal. Put 3 holes at the same horizontal depth, right? Right? Put 3 holes at the same horizontal depth, and what should happen? It should come out the same, right? So it should come out the same distance, right? Let's assume that they all travel the distance x. Are you okay with that? Just make a note of that now because it's 2 popular experiments, right? All right, so pressure, different depths will vary, pressure the same, depth is the same, right? Make sure if they ask you to do a small experiment that you can redraw and explain this, right? Okay. It's real simple. You just have a container, put 3 holes at different depths, and tell them which one will come out the furthest. Excuse me. Sorry. All right. We will come back and do like this atmospheric pressure example. I just want to talk a little bit about Archimedes' principle. All right. Let's see if we can look at this simulation real fast, right? I just wanted to understand the theory behind Archimedes' principle. All right. This one do have the displacement. Can't. Hold on. Let's not give me one more chance, right? All right, now this simulation's not good enough. All right, so here's what we're gonna look at, right? Here's what Akademi said, right? If I give you a displacement can, right? The displacement can, obviously, it just allows water to be displaced, right? Right. So here's what Akademi says. Here's what Akademi said. Akademi said is that he said that if you place an object in here, right? Right? If you all take a ball, for example, and try to put a ball down in water, what is something? The water does rise up, or the ball is have a kind of upward force on it. Right. So that upward force is what we call upthrust. Right? And what Akademi said that upthrust, that force you're experiencing, is equal to the water that will fall out here, the weight of that water. So when you put the object in there, obviously the object will push out some water, right? Akademi said that the upward force was equal to the water that fell out. That's okay? That's basically what he said. He said that the upthrust was equal to the weight of fluid displaced. Right? Which simulation this was? I remember this was a PhD. Yeah, sorry. What's that? I've nothing to do it. Yeah, I put the water. How you could only displace its own volume in water. Okay? But in short, that's basically what Akademi said. Akademi said that the upthrust, which is the upward force, or sometimes we call it the buoyancy force, right? The upward force or the buoyancy force is called the upthrust. Okay? Just make a note of that. Now, this is Akademi's principle. I gave you the worded version. I want you to just make a note of this. Yep, I'm sure now. Ready? Finish this. All right, nice. So let's put some numbers in it here, right? So I want to give you the same scenario. The objective is to find the upthrust, right? When the object is inside here, what are the two forces active? Upthrust and weight, right? Let's pretend the weight is 10 newtons. I don't know what the upthrust is. Right? We're not sure what the upthrust is. But I am going to connect this to what we call a spring balance. Right? And the reading on the spring balance, is 2 newtons. What do you think the upthrust might be? Spring balance measures the force. What do you think the upthrust might be? You see what you're glad of you. Right. What's the guess? Any guess? Well, here's the thing, right? The spring balance, we're going to measure the resultant force, right? There's a downward force of 10, upward force we don't know, but we know the resultant. We know that the resultant is 2 newtons. So, yeah, think about it like this. That 2 newtons represents W minus U, right? W 10 and U is 2. Sorry, U is, we have no idea. So 10 minus U is 2. So how much is U? How much? Well, 8. That's now here 716. Yeah, 5. I didn't hear 716. 716. Answer is 8. 10 minus 8 is 2. And Nathan? Newtons. Newtons is a force. Okay, so remember that, right? The scale always measures upthrust minus weight. All right, let's go again. This time here is 12. Here we don't know what it is, but here's 6. Here's 8 newtons. U is how much? How much you got? I'm only getting 5 here. One answer. I will change the still. You'll get 5 in the next one. What's the answer? 4. 4. 4. First 5. Let's go again. This time I do not know. This time I don't know what the reading on this scale will be. What's the reading on the scale? Huh? 8 newtons, right? Good. I'm going to change the scenario again. Now you have to apply your knowledge here, right? Water fell out. And the weight of the water is 7 newtons. What is the upthrust and what is the reading on the scale? Think about it. What is the upthrust and what is the reading on the scale? What is the upthrust and what is the reading on the scale? Right? Message them together, right? Anya? Cherubi? You have to write it down. Write it down for me now, please. Number 3. Write down what the weight is, what the upthrust is. And the first picture you outside, don't let anybody let you in me. Outside. How much y'all got? Upthrust is what? Upthrust is the same as the weight of fluid displaced. And the reading on top here will be 12 minus 7, which is 5. Don't forget a sign outside. Right? Don't forget a sign outside. Right? Next one. Oh, by the way, how you find weight again? Mass of what? Mass of the fluid by gravity, right? Are you okay with that? I just have one more thing for it, just one more thing to find out, right? We said upthrust is equal to mass of fluid by gravity. How else we can find mass? Anybody remember our formula from the beginning on mechanics to find mass? Anybody remember? There's our next formula for us to find mass. Mass is what? Right? Mass is equal to volume by density. Okay? Mass is equal to volume by density. Okay? You all might remember this. Might. Density is mass on volume. Huh? outside. Okay, and that's one of the main things I want you to remember. Yeah? See this version of upthrust. Upthrust is equal to volume of fluid by density of fluid by gravity. That's the next version for upthrust. Sometimes we kind of forget this version as well. Huh? Why is it? What do you mean? Upthrust is mass by gravity. Right? Yeah, no, this is the formula for mass. Okay? So theory-wise, oh wait, no, sorry. I can't tell you that as yet. Right, so remember that. I'm gonna change some numbers now and I want to try to figure it out. All right? So I've given you an object. The object fully submerged in water. I am going to give you the upthrust. The upthrust is 5 newtons. The density of the water is 1,000 kilograms per meter cube. Find the volume of the fluid displaced. And the volume of the solid. Hey, we're doing. When you come here, do I end up talking on the phone? You want to put on your headphone, put on your headphones. All right? Are you done? Yeah, you gotta find what the question asks in here, right? So you're not done. Yeah, calculate it now. All right, let's see what we got. How much you all got? Diana, how much you got? 4, 5? So upthrust is what? We said upthrust is density by volume by gravity. We know the upthrust is 5, density is 1000. We don't know the volume, and we know gravity is 10. That's okay? So it means that volume of water will be 5 over 1000 by 10. Right? That's what the volume will be. How much is that? That's 5 by 10 to the minus 4. Anybody got that? 5 by 10 to the minus 4 meter cube. Meter cube because it's volume. Right, but and I was kind of hoping you all figure out that part. What about this part here, the volume of the solid? What would the volume of the solid be? If we got the volume of the water to be 5 by 10 to the minus 4 meter cube, what do you think will be the volume of the solid? Nathan? Have a guess? Form 4 class. I'll give you Form 4 a chance. That's what I do this. Kilan, how you doing there? Huh? Any ideas? Caleb? Jose? Ashton? So if you put an object in water, right? And it displays some water. What do you think the volume of that water represents? Same volume as the object, right? So what has always happened? An object that's fully submerged will always displace its own volume. Okay? So if the volume of the water that was displaced is 5 by 10 to the minus 4, then the volume of the solid is the same thing. All right? So make a note of that. An object will always displace its own volume in water. Sorry, its own volume. An object will always displace its own volume when fully submerged. Right? When fully submerged. Yeah. Yes, no. That's yeah. What's that? So when the ship well technical, but not significant. All right. All right. So here we have 3 scenarios, right? And as I told you before, the 2 main forces acting on the object is The two main forces acting on the object is upthrust and weight. All right. Here we have three scenarios. I would like an object to rise in water. I would like an object to sink in water. And I would like an object just to float. Right? So my question, Gianna, which of those has to be larger? The upthrust or the weight for it to rise in the water? The upthrust, correct. The upthrust must be more than the weight. Ashton, for the object to sink in the water, which one is larger? The weight has to be larger. And if the object has to float annually, what do you think have to happen? Upthrust equal to weight. You're going to say that, can't you? Upthrust equal to weight. If you have to remember, one is the float. That's the most important one. Right? You have to remember that floating part there. Upthrust equal to weight. Okay? So those are conditions there for something to rise, sink, and float. Anybody have an idea how the Annalie, your lesson, Nuria? What's one ask sorry again? Anybody have an idea how a submarine works? Caleb, think about it. How does a submarine sink and float? So the submarine on top of the water now, upthrust equal to weight. It wants to go down. Why do you think this happened? Right? Change the weight. How? If you had a guess. Help them set it. Right. They have something called ballast tanks that'll take in water. And it will take in the water, causing the weight to increase, and it will sink. And if you want to go up, it will remove the water. That's okay? So that's the way how it works. That's the way how it works, right? So theory-wise, that's everything that we need to know in mechanics. All right? Those are the things that we need to know in mechanics. So what we need to get, for sure. Right? What we need to get now is a little summary of everything in mechanics. All right? So I want you to come on the board now one at a time and write something that you learned about mechanics. Right? Something that we learned about mechanics. All right. So if you're looking in group here, I have a whole summary I'm going to send. Right? There's an old summary I'm going to send. And it has all the topics, but we didn't learn everything as yet. Just take a look at the mechanics part of it, right? These are all the things that we need to know in mechanics. Yeah, mechanics is the longest. Hold on, I'm going to unsend it. I'm going to unsend it in the group, right? All right, so watch here. So these are all the things that we need to remember from mechanics, right? We need to know about derived quantities, SI units. All people who have labs are like this separate now. After this, right? You have to write this down. Okay, after this, I'll look at next door. Okay, right? We have to remember all the quantities and base units. We have to remember all our prefixes. So if you see micro, you have to remember micro. You have to be able to draw a graph properly, right? Every time you draw a graph, it should look like that. right? Nice best fit line, find gradient, and so on. We should know about errors, right? We should know about errors, right? So whenever you're doing a lab, you should be able to say, okay, well, during the lab, I had a random error because I didn't take the reading high level. I have a systematic error because the micrometer not working, right? So whenever you look for source of error, just think, okay, were there any random errors? Like the pins that go to the reflection, the pins were bent, the mirror wasn't stuck on to the wood properly. All those small things will throw your angles off. So if, for example, you do a lab, right, and you end up with perfect values, but there were systematic errors, then we will know you do what? You do all the reaction, right? But then we'll go back and put it wrong. Okay? So that's I was telling somebody, you do a lab, you follow the instructions properly, but you end up with the wrong results. Nothing wrong with that. Explain to them why it's there. Explain to them what happened. The person who doing it was blind, or the mirrors had a broken line in them, all those little things. Once you can explain why your bars are slightly off, nothing wrong with that. Okay? You should know about density, relative density, scalar and vector quantities, and be able to find the resultant force. All right? Moments, right? Know your principle of moments, all your formulas, center of gravity, how to find it. We should know about linear motion, velocity, acceleration, and so on, right? From that, you should remember your graphs, time graphs, how to apply it, right? Laws of motion, laws of momentum, right? Make sure you can explain all Newton's laws. Make sure you can explain momentum, okay? After that, we did energy. We talked about different types of energy, two main types, kinetic and potential. We talked about power, and today we did the last thing, pressure and academic principle. All right? So what we're going to do now, we're going to start doing some revision on questions. All right? People with labs, or like head across in the lab. People without labs, or like sit down. Form 5, or like here till 1 o'clock. Form 4, or like leave at 30:30. Huh? Real time. 12:13. So your class didn't start yet, so sit down right here until the class starts. Hey, I had to get your mother number in the book. I'm getting the time. I still had to get your mother. Sorry? Who said that? Cheryl? No, you haven't. You here until 1:30. Yes, ma'am. All right. So let's start. Right? We are going to start with multiple choice. All right? Let's start a revision with some multiple choice. Hey. Your boy don't need no help. Sit down right there. Right now, you're doing work. Sit down. Sit down. No. You don't want to see it. All right, so let's start with this multiple choice here. That's now. Organize and make sure you all do all those last two. And we're using water instead first. We're doing the specific heat capacity of water. All right, sorry. Let's start June 2021. Hope you all could see it. Do the one thing you can see, right? Sorry? You can't see now? No. You hear multiple choice, but you ask them a paper. I just get full screen again, boy. Why so small? All right. So we're doing 1 to 5. Yeah. Every minute and a half, you just move it up, right? 1 to 5 and a corrected. Joshua, so we have labs today, right? Yeah. Oh yes, every minute, just move it on, right? Go ahead. Just write the number, write the answer. So if you need working, you need to see these? Yes. So you can get that back. Come on now, you in charge. 1, then 2. Every 2 minutes. Look at the fire. Yeah, every minute and a half, change it, right? Right? Oh yeah, 1 to 4. 1 to 5. Number 1, 4, and time up to number 1. Wow. Control time? Yeah. All right, let's go. So analyze all that. All right, number one. Too bad, too bad. We had to continue. We had to do all the whole. Number one is what? C. Right? Number one is C. Good. Work done on time. Due to parallax, or errors due to parallax can be minimized by which one here? Placing the eye at right angles. All right. B is the best answer. Yeah. B is the best answer. Which of the following are fundamental quantities? Which one? Mass and length and time and current. Yes. Dog. Number four. You have nothing in the book. Number four. What should be the magnitude and direction of a third force, which will make it stationary? Which one? Yeah. Which one? X and Y to the left. Correct, right? If you have a force acting to the left, X plus Y, that will balance it off. Number five. Oh gosh. Stop chipping later and downstairs. Hey, I tell I go and put you outside, but if you're talking right, sure, I'll stick it on the wall outside. All right. What you all got here? Oh no, this thing's stick. You're not seeing the answers? See that coming out. This thing stick here, boy. What was it? Which of the following equations must be true to be stationary? L squared is equal to m squared plus n squared. Answer is A, apple. Oh, wait. I don't know what A is. A was what? That's wrong. Hold on. Yeah, the answer is A, apple. I was a relics. Next one, this thing stick, right? So I just share it over. Oh wait, the whole thing stick, wait. Hey. All right, sorry. All right, let's go again. Which of the following can be caused by a force acting on a body? So you have a force acting on the body. Can it change the shape? Can it change the motion? Can it change density? Can it change the shape? Yeah, if you apply a force. Can it change the motion? 1 and 2. Can it change density? Density is what? Density is mass over volume. Can it change the mass by applying a force? No. Can it change the volume? No. It'll be the same volume. So therefore, the answer is what? Apple. Okay. Next one, number 7. Oh, wait, you're not seeing everything. Right? What you all think? A, B, C, or D? What you all think now? Which one? So you have the following. You have P and Q with different water levels connected by a glass tube and controlled by tap. When the tap is open, water will flow from P to Q until what? Until the P is empty, no? No. Until? Dog, yes. Until the water levels in P and Q are the same. Why? We talked about it a while ago. Why? We talked about it at the beginning of the class. Why is the answer dog? Annalie? Any guess? Why? So when they both are the same, what happens at the same depth? Pressure is the what? Pressure is the same, right? So if the pressure is the same on both sides, can the water move? No, water won't move. All right, so that's it there for the form 4s. Form 5s, finish out the rest of the summer, please. Pressure the same depth. All right, form 4s, that is it. Form 5.